Today we're talking about reading and writing in scientific notation. You may have done this in science class, so hopefully this is a review. Scientific notation requires two things. There's one digit left of the decimal point, and that it's being multiplied by a power of 10. In this case here, with this number, 135 million, right away we can see there's way more than one number on the left of the decimal point. Therefore, it's not in scientific notation. When we write it in scientific notation, we have to imagine, okay, here's the decimal point that's here. We have to find out what power of 10 it's being multiplied by. So what I'm going to do is I'm going to make like a little scallop here and go 1, 2, okay, I went 8 times to the left so I can put my decimal point here so that there's one number on the left of it and everything else is on the right. I would rewrite this then by saying this is the same thing as 1.35 times 10 to the 8th power. You'll often see this written on calculators as 1.35 E8. Similarly, if I have the number 0.000135, I'm going to do the same thing. I want to get it so that there's only one number on the left of the decimal point. So counting, and this time I'm going to the right. I went 4 times to the right. So I'm going to rewrite this as 1.35 times 10 to the negative 4, or 1.35 e negative 4. If you'll notice here, in this first example, when this number started out being very large and I moved my scallops left, my exponent is positive. If I'm moving my decimal to the right, and this number started out very small, the exponent is negative. If you'll remember from our exponent lessons that we just did, because this has a negative exponent, what this is actually saying is we're flipping it over the bar, and we're actually multiplying it by 1 over 10 to the 4th. So this is showing that this is this normal number, 1.35, divided by a very large number, which if you were to do that, you would end up with a very tiny number, like this. So just a quick example, if I were to ask you to write this in scientific notation, the first thing we see is that it's a very large number, which means the exponent will be positive. So we're going to count how many times we have to start at the end and move our decimal to the left. Okay, so I moved my decimal 11 times to the left. So I rewrite that as 4.38 times 10 to the positive 11. What happens if I end up with something like this? Here I see that it's not written in scientific notation. This is 23.7 times 10 to the 5th, but there's 2 numbers in front of the decimal. In order to convert it to be in scientific notation, what I would have to do is take this and move it once to the left. Remembering from just a couple of minutes ago, I know that if I'm moving it to the left, I'm making it technically smaller. I'm making the number 23.7 into the number 2.37, which means that if I'm moving it to the left, I'm going to add 1 to the exponent, so then when I multiply it, it goes back to being the proper number. So I'll get 2.37 times 10 to the 6th. So you can think left is positive, right is negative. In a way, it's kind of canceling itself out. The smaller you make the number, the bigger the exponent has to be. And the bigger the number, let's do another example where I kind of demonstrate the balancing act that you're doing. In this case, it's not written in scientific notation the other way. This number is too small, so we have to move to the right twice to make this tiny number into a larger number by a factor of 2. Because I'm making the number bigger by a factor of 2, so now it's 4.3, I have to subtract. To balance it on the other side, I subtract 2 from the exponent. So now I have 4.3 times 10 to the 8th. So just a quick recap, if you're making the number part bigger by any factor, the exponent decreases by the same factor. If you're making the number smaller by any factor, then the exponent on the 10 increases to balance that out.